Welcome to this short explainer video where we're going to look at how to apply Kirchhoff's laws to slightly complex situations. I'm going to assume that you have read about Kirchhoff's laws and that you already have a good understanding of how circuits and currents work. So let's get started. We're going to look at this circuit you can see on the screen during this video. We've got a bit of complexity in that our wires are somewhat sort of curiously arranged. We've got a couple of cells or a couple of batteries in here, a couple of resistances, and then we've got obviously our currents coming in and out. And it could look quite daunting. What I'd hope to show you is that these problems can be separated out and boiled down into slightly simpler problems, which hopefully will allow you to solve for whatever you're trying to solve for. In this case, we're trying to solve for the following. We want to know the value of I1. Now what we're going to do is so it's the current number one. What we're going to do is we're going to use a couple of different approaches to see what we could do, and then hopefully settle on one which is the sort of easiest to understand in a relative sense, obviously. I encourage everybody when they're starting off with Kirchhoff's laws to think about both laws. So let's think about Kirchhoff's first law, which states that the sum of the currents going in or out of a junction are the same. So the current in is equal to current out. Now if you look here, we've got a junction which kind of labelled for us, junction P, and we've got two currents coming in, I1 and I2, and we've got one current coming out, which is I3. If we take those currents going in, that's I1 plus I2 is equal to I3. That's just our Kirchhoff's first law. And the reason we're setting this up is because it may be that actually we can solve this problem very easily. It may be, for example, that I1 is equal I3. However, it's pretty clear here that we're quite complicated situation. I1 plus I2 equal to I3. We want I1. We're going to have to know some more information before we can solve that problem. Now, one way of getting that information would therefore to use Kirchhoff's second law. Kirchhoff's second law states that we've got the sum of our EMFs, that's the energy into our circuit, is equal to the sum of the potential differences, that's the energy out, around any closed loop. And it's that key phrase, any closed loop, which we're going to apply in a second. Now this problem, we've got two EMFs. Those are supplied by the battery. So we've got the batteries, I should say. We've got a 6 and a 2, and notice that they are connected in opposition to one another, and so therefore we might have to think about that when we're going around a loop. And we've also got two potential differences. The potential differences can be calculated by thinking about our Ohm's law. We're assuming that we've got perfect conductors. Okay, we've got a 30 ohm resistance with a current I3 going in it, so we've got 30 times I3. And then we've got a 10 ohm resistance with a current of I1, and so therefore we've got 10 I1. That's our potential across the both. Okay, we're well set up to use Kirchhoff's second law, so let's try and choose a loop. Now let's start with this one. We've got a very clear loop which is begins and ends at the 6-volt battery. Okay, remember a closed loop can be any path around the circuit which begins and ends at the same point and doesn't repeat on itself. And so therefore, if we begin at our 6 volts, we come out of the left hand side of that battery, go down and then take a sharp right at P, follow through the 30 ohm resistance, back up the 10 ohm and back into the battery. That's a closed loop. Let's have a look at our, this is a loop you might choose because there's one battery, we don't need to worry about this opposition, and we can just get our numbers out. Now what you've got there is that the sum of the EMFs on the left hand side, that's 6, is equal to 30 times I3, that's our potential difference across the 30 ohm resistance, and our 10 times I1, which is the potential difference across the 10 ohm resistance. Now you can see again, we've gone some way to finding our I1 value. However, it's going to take us a lot of extra work. We don't know I3. We also don't know I2, and so it doesn't really help us doing this loop. There is, however, another loop that we could use, and I'm going to show you that this is a much, much more useful one. The loop that we're going to use is this one, which instead of taking a right through the 30 ohm resistance, is actually going to go down through that second battery and then up back through our 10 ohm resistance and then through our 6-volt battery. Now a lot of students stay away from this loop because of the fact that the two EMFs are opposing each other. Well, when they oppose each other, all we have to remember to do is subtract one of them. And we subtract the one that we're entering into. Now, if you notice here, we left the 6-volt battery. We're going anti-clockwise. We're leaving the 6-volt battery, and we're going very much into the 2-volt battery. I'll talk a bit more about direction in another video. And so therefore, we say that we are got positive 6 and a negative 2 here. We have a positive 6 EMF on this side and a negative 2 EMF on this side. And then we go back up through and we rejoin the previous loop, and so we've got one potential difference, which is going to be 10 times I1. Now notice here that we now only have one unknown in the equation, namely I1. And so actually I can do my maths, and I'm left with I1 equal to 0.4 amps. So you notice that with the pain that we went through to get those two other equations, Kirchhoff's first law and Kirchhoff's second law, was actually avoidable simply by choosing the correct loop. Now, I'm not saying that every physics question is as easy as this, as easy to solve in this way. We may have to combine two things together. However, you should be aware that there are more than one loop in a circuit. Namely, in this one, we actually have 3 loops. We have the 2 that we've considered, and then we have that bottom loop as well. And we haven't chosen the bottom loop here because that wouldn't help us calculating I1. It would, however, help us calculate I3, and I'll leave that as an exercise for you guys to get on with. Okay, I hope that helps, and as ever, please let me know if you have any questions.